Hey everyone, welcome back to my another tutorial. So this time I will talk about TensorRT and object detection with YOLOv4 and how we can increase speed and optimize our YOLOv4 object detection model. So we already discussed YOLOv4 improvements from its older version YOLOv3 in my previous tutorials, and we already know that now it's even better than before. Probably everyone who used YOLOv3 will move to YOLOv4 because it's one of the fastest object detection models that we may use for real-time applications. But in this tutorial, I would like to show you how we can increase the speed of our object detection up to 3 times with TensorRT. But I should mention that in this tutorial, I will not cover how to install TensorRT. So, TensorFlow is one of the most popular deep learning frameworks today, with tens of thousands of users worldwide. Talking about that, TensorRT is also a deep learning platform that optimizes neural networks models and speeds up performance for GPU inference in a very simple way. So the TensorFlow team worked with NVIDIA and added initial support for TensorRT in TensorFlow 1.7, and now it's already in TensorFlow 2.0 and above versions. So I chose to use it for my own project and to test how it performs. So what is TensorRT, you may ask, if you never heard about that. And of course, you might find a lot of links in my text version tutorial where you can read about it, but I will mention that that's a high performance inference optimizer runtime that can be used to perform inference in lower precision. Lower precision is FP32, FP60 and int8 on GPUs. TensorRT integration with TensorFlow lets us apply optimizations to our TensorFlow models with a few lines of code. I mean, to convert that model. With TensorRT, we can get up to 8 times higher performance than using only a TensorFlow. The integration applies optimizations to the supported graphs, leaving unsupported operations untouched to be natively executed in TensorFlow. So you may ask how the TensorRT optimizes TensorFlow graph. So usually we input our already trained TensorFlow network and other parameters like inference, batch size and precision. Then TensorRT does optimization and builds an execution plan which can be used as in serialized and saved to disk. Then it can be used at a later time, same as usual TensorFlow model. I haven't tried, but I think that a deep learning framework is not required at inference time. We can just use the execution plan output by TensorRT and we are good to go. We can use it on servers, desktops, or even on embedded devices, right on documentation. So here is a simple TensorFlow workflow shown in this slide. Next is the optimization process, and this is where the magic begins. TensorRT performs several important transformations and optimizations to the neural network graph. So I will show you several slides about that, and TensorRT, where possible convolution, bias, and ReLU layers are fused to form a single layer, and here is shown an unoptimized network graph. So next figure explains the vertical fusion optimization that TensorRT does. Convolution, bias, and activation functions, ReLU for example, respectively is called CBR, as you can see, and all these layers are all collapsed into one single node. This would mean a single CUDA kernel launch for C, B, and R. Another transformation is horizontal layer fusion or layer aggregation, along with the required division of aggregated layers to their respective output. Horizontal layer fusion improves performance by combining layers that take the same source tensor and apply the same operations with similar parameters. Note that these graph operations do not change the underlying computation in the graph. Instead, they look to restructure the graph to perform the operations much faster and more efficiently. So here is the final optimized horizontal fusion. from TensorRT. As you can see, there is much lesser layers than in slides before. So next, I will show you how I implemented TensorFlow to TensorRT conversion function in my model. So suppose we already have a trained TensorFlow network. First, we convert that our model to the frozen model. So, and right now I'll show you how I do this in my YOLOv4 implementation. So here is my GitHub implemented function. I'm showing you on the gist because I actually posted my implementation to more sources, not only here. So that's a little simpler to show you. So usually I simply load my standard YOLOv4 model in Keras, the same as everyone do, and we simply call a YOLO.save function. And this way our frozen model will be saved to PB format. Now that we have our working frozen model, in order to get the benefits from TensorRT, we need to convert it to a model that runs the operations using TensorRT. I also have a function, so using following correlation commands in my implementation, we can achieve these steps. The main thing what we should do, we should specify the conversion parameters when converting our TensorFlow model to TensorRT. So simply there is a few parameters I can explain. One of them is precision mode that tells converter which precision to use currently, and it is supported formats as FP32, FP16 and int8. So, and you specified this in my configs file. I can open it actually. And here is YOLOv3 and configs, and you should specify the YOLO TensorRT quantize mode. Next is max batch size that tells the maximum batch size of the input. The converter requires that all tensors that will be handled by TensorRT have their first dimension as the batch dimension, and this parameter tells it that the max value will be during the inference. If the actual max batch size during inference is known and this value matches that, the converted model will be optimal. Note that converted model cannot handle inputs with batch size larger than what is specified here before conversion, but smaller, everything is fine. Next is max workspace size bytes. This one. And that's an integer and maximum GPU memory size available for TensorRT. So we should set it to, I don't know how many zeros there is, 4 and 9 zeros, and we should set it for 12 gigabytes GPU in order to allocate around 4 gigabytes for the TensorRT engines. And next one is a calibration. This argument is ignored if precision mode is not int8. If it is true, a calibration graph, if we use int8, the calibration graph must be covered to an inference graph while converting TensorFlow to TensorRT by giving calibration input with calibration data. If set to false, the quantization nodes will be expected for every tensor in the graph, and if a range is missing, an error will occur. Why we need calibration? Well, actually we'll talk about it later. And about other configurations you can read on my text version tutorial. I'll try to cover them in README file. So let's move back to my YOLOv3 GitHub implementation. As you already should have understood from this tutorial title, I cover converted YOLOv4 to TensorRT, all available precisions. I filled a table below with where it is. Let me find it. Here it is. And we now can compare their FPS and mean average precision performance. These results were measured on 1080 Ti GPU. So first I would like to say that it was quite strange for me that FP16 was a little worse performing than FP32. We can see this from following FPS table here. The map was actually the same because FP32 and 5060 have a large number after the decimal point, so there is no significant change. But when we look at int8 map, we see quite large drop. Here is the map. We can see a quite large drop in model accuracy. This one is YOLOv4, and here is mean average precision. So as you can see, if we achieve 37 frames per second on following the input dimensions, we achieve only 55% of mean average precision, while in FP32 we achieve 64% of mean average precision. Well, compared, that's quite a lot, but when we see how much frames per second we win, so actually everything depends on what purpose you will use object detection model. You need to decide, you need accuracy or more like a real-time detection speed. You can try to find the gold point that fits for you between accuracy and speed. I would use YOLOv4 int8 model with a large input size, following probably, because this would keep a quite high accuracy and speed that I could use for real-time detection. And what more, I would like to add that while using object detection, execution time, power and accuracy are critical in real-time applications. Given the amount of computing required, we would like to optimize our inference in favor of time and power without hurting the accuracy. So we can move to an 8-bit representation of parameters and activation at inference time. And as you can see from following results, the 8-bit inference needs a lesser cycle for memory to fetch compared to a 32-bit. As a result, speed increases twice, but we lose about 50% of accuracy, as you can see. And this is 63 and 54 is around 50%, but speed increases more, well, a little more than twice. It depends on what GPU you use. The main question is how TensorRT optimizes neural network to get that results. TensorRT with int8 precision mode just needs to implement an inference that provides calibration information and some catching related code. Before that, let's see the steps TensorRT follows to do the 32-bit to 8-bit mapping. The candidates for mapping are inputs to each layer, which would be input to the first layer and activation for the rest, and learning parameters. The simplest form for mapping quantization is linear quantization. Here I showed a linear quantization function at first line, and as you can see here is FP32 tensor equal to scale factor multiplied by 8-bit tensor, and we add FP32 bias, and we can make it simple. Experiments have shown that the bias term does not really add any value, so we can get rid of it, and then we receive that FP32 tensor is equal to scale factor multiplied by 8-bit tensor. SF here is the scaling factor for each tensor in each layer of the layers. The problem here is to find the scaling factor. You can read more about details about the whole process in NVIDIA slides, and the link is on my TechVenture tutorial. But authors suggest one simple approach as shown in the following slide. In this slide is shown a simple map of minus max and max FP32 value in a tensor to minus 127 to 127 respectively. The rest of the value are linearly scaled accordingly, but experience showed that this kind of mapping results in significant accuracy loss. So TensorRT tried to do following instead. Looking at this slide, you can see that the max values were used as a fixed threshold and then were mapped as before. Any value that lies in the threshold is adjusted to either 100 minus 127 or 127. For example, in this slide, the 3 red crosses are mapped to minus 127. But the next question is, how do they find that optimal value of threshold t? So we have a FP32 tensor that are best represented in FP32 distribution. But we want to represent them in different distribution, 8-bit, which is not the best distribution. We want to measure how different these distributions are and want to minimize that difference. TensorRT uses a Kullback-Leibel divergence, KL divergence shortly, and the link is on my text version tutorial, to measure the difference and aims to minimize that difference. So our goal is to minimize the KL divergence between FP32 values and corresponding 8-bit values. TensorRT uses a simple iterative search for minimum divergence. The steps are following. So first we run an inference on calibration dataset, and for each layer we collect a histograms of activations, generate many quantized distributions with different saturation threshold. We pick the threshold which minimizes KL divergence, and entire process takes a few minutes on a typical desktop workstation. And if you saw on my code, which I showed before, there was a calibration. That's exactly why it is needed. I would like to talk a little more about info calibration. It aid calibration. In TensorRT employs an experiment-based iterative search for threshold values. Calibration forms the main part of it. We provide a sample dataset. Ideally would be a subset of validation set called the calibration dataset, which TensorRT would use to do what is called a calibration. TensorRT runs FP32 inference on the calibration dataset, collects histograms of activations, and generates a set of 8-bit representations with different thresholds and chooses the one which has the least KL divergence error. The KL divergence is between the reference distribution, which is the FP32 activations, and the quantized distributions, which is 8-bit quantized activations. So that's it shortly. More about int8 and precision in NVIDIA GPUs you can read on the link on my text version tutorial. So right now, I would like to show you my practical YOLOv4 TensorRT implementation, and as I told you before, I will not be showing how to install TensorRT. It has many dependencies for what OS you use, what CUDA version, what drivers, and etc. The best way is to Google it. So if you already have installed TensorRT, you can try my YOLOv4 TensorRT implementation and whole conversion process, which is written there. So actually, let's go to my GitHub, and first you should download the weights, of course, and you should try the demo script, detection demo py, and this way you will understand if this implementation works on your computer and you have everything installed correctly. Then there is a tools folder where I placed these conversion scripts. So one is to frozen model, one is to TensorRT graph. So before using them, we need to change a few lines in the configurations file. Let's go back, and my configurations file is here. So actually, I will convert model to YOLOv4 with input size 608 to the TensorRT and int8 model. So actually, I have already tried this while developing, and I can open it. And as you can see, there is YOLOv4 TensorRT. At first, this should be false while you are trying if everything works for you, and here is 608. So you should change these parameters accordingly to your needs. Now we need to convert a YOLOv model to the frozen PB by simply running a Python script from here, calling tools and convert to TensorRT, or simply open this and just run it. everything depends on the configurations in configs file. When it finished, there should be in checkpoints folder a new file called YOLOv4 608. Here all are my examples which I were testing and measuring the performance. After this, when we have this model, as you can see, and when the conversion finishes in the checkpoints folder, you can find this folder. So this is the frozen model that we'll use to get the TensorRT model. To do that, we also call another script. So we use this one. Also, all the configurations again depends from here. And now this might take a while, 5 to 10 minutes. It depends on what GPU you have, but when it finishes, you should see a new folder in checkpoints folder. So I can open it. Sorry. So this would be this folder. Now you can test it the same way as with the usual YOLO model. Once again, open config.py file, and now when you have converted it, you should simply remove this, and that's it. Here is our frozen TensorRT model. We change here our configurations. So actually here should be written our TensorRT model location and name, which we are planning to run. Now we simply can run a detection demo file. Actually, where it is, detection demo, and that's it. Best way to test is run on detection video, and actually I think I can run it. And here is the detections shown in real time, and as you can see, here is my frames per second. Here is 35 frames per second of detection, and here is with a driving bounding box. So I'll hope to fix the drop with driving detection with multiprocessing or by optimizing my code. And actually this is a quite satisfying results. And next we can run actually an object tracker. It should also work. This is on 1080 Ti, I should mention. So here's my object tracker. Here it is. Okay, I'll run it also. Let's wait a moment to it to open. So as you can see, we also receive quite nice results. Theoretical detection frames per second should have been the same. The total F frames per second is lower. It's okay because tracker runs two models, one for detection and one for tracking. And also keep in mind that these frames per second are for 800 by 800, I mean 608 by 608 input size. And so all in all, there is plenty of scope for optimization TensorFlow framework. Given TensorRT optimization and the right hardware, which depends on DP48 architecture, you can not only push the GPU to its limits, by the same time keep it efficient if you would understand everything in details. So also, as a demonstration in this tutorial, the performance numbers only apply to the model that I am using and the machine that runs this example, but it does show the performance benefits of using TensorRT. And I believe you'll see substantial benefits by integrating TensorRT with TensorFlow when using NVIDIA GPUs. Additional information on TensorRT can be found on NVIDIA's TensorRT page, and the link is on my text function tutorial. Also, I tested TensorRT not because I wanted to write this tutorial, but because I wanted to come back to my old shooting game tutorial. Let me show you. Where is the Brave browser? If you were following me, you should remember that I implemented aimbot for Counter-Strike Go shooting game, and I couldn't do any improvements because of low frames per second. Now, when I have tested TensorRT benefits, its frames per second improvements, and I have an even better YOLOv4 model than YOLOv3, and of course my experience increased in programming, I'll test this out. I hope these benefits will make my aimbot even better. So wait for it in the coming tutorials. Also, I forgot to mention, for those who would like to convert TensorRT of their custom models, I'll write steps for you what you should change in your configurations if you would like to convert your custom training model, because this is a little different than using this default configurations of mine. You should change a few more lines to get your needed results. So that's it. Thank you all for watching. I hope this tutorial was useful for you, and hope to come back to you soon with a great new interesting tutorials. Subscribe, like, share, and see you next time. Goodbye.